Dear students, today I am going to present to you the integral analysis in the chapter of boundary layer theory and its applications. So let us first get down to the objectives of the class. So firstly, I will introduce two terms which are called as displacement thickness and momentum thickness. These are integral terms for integral analysis of boundary layer theory and thicknesses. I will explain the physical interpretation of these terms, and then we will go on to derive the von Karman momentum integral equation. Now this von Karman momentum integral equation is just the integral form of the momentum boundary layer equation, and then I will use these two things, that is the momentum integral equation and the displacement and momentum thickness to to generate the first predictions of boundary layer thickness, drag, and friction forces, friction factor, skin friction coefficients. So let us go down to this. So this is the setup. So you have a flat plate and then the flow over a flat plate. Now, before going into the mathematical details, first we will try to explain what is the physical interpretation. So consider a flat plate over which there is a flow, over which there is a flow in x direction. Now consider a section, uh, which is we will name the section as A, and if this suppose there is no boundary layer present at this section, then there is the flow will be uniform, that is inviscid. So if u infinity is the inviscid velocity, then the profile at this section will be u infinity. Now if I consider a streamline, so the streamline for all the undisturbed region, that is if the supposing the boundary layer is not present, will be a straight line. Now um, uh, if we consider the boundary layer, now so the blue line shows the boundary layer development. Now because of this boundary layer development, if I now draw the same streamline, it will um, show a slight bend in the streamline curvature. Now this streamline curvature bend shows that the the fluid which is at fluid which is inside which was inside the boundary layer is being deflected upwards. Now if I draw the velocity profile at a section B, then inside the boundary layer this will be the velocity profile, that is the parabolic normal velocity profile, and where delta is the thickness of the boundary layer. Now and above that there will be a constant u infinity. Now if and let us consider this length for which the velocity profile is deflected as the delta star. Now if I try to write down the mass flow rates as these two sections, that is at section A, then mass flow rate will be rho naught into delta into u star u infinity, and at section B there will be two parts. First will be the velocity integral from 0 to delta, and integral delta where u is a varying velocity profile, plus the compensated part, that is the rho naught delta star into u infinity. Now since by mass conservation the the mass flow rate at this section, at the section A and section B, should be equal. So if I place this equivalence, and then we get the value of delta star as 0 to delta 1 minus u by u infinity. So displacement thickness basically represents the compensation in length to maintain the same mass flow rate, which is mass flow rate due to the development of the boundary layer. So that means that if the boundary layer is developed, since the boundary layer is developed, if you want to have the same mass flow rate, then this velocity, then this length is basically the compensation. So if I go to the full mass flow rate, so the change in mass flow rate, if I do not integrate from 0 to infinity, if I integrate from 0 to infinity at these two cross sections, the mass defect will be 0 to like this. It can be written from like this. So you can see that delta m is equals to rho naught 0 to infinity ux into minus ua. So now you can say, so displacement thickness basically represents the defect in the uh, in the mass flow rate. So similarly, if you have the similar constant range, yeah. Now if I write down the momentum flux at these two sections, JA and JB, so JA will be nothing but rho naught delta into U infinity star, and JB will be rho naught 0 to delta U square into U square dy, um, integral U square dy plus rho naught into delta star and U infinity square. Now if I plug calculate the momentum deficit, so the momentum deficit will come out like this. Now if I plug in the delta star value, then it comes out this. So theta, which we call as the momentum thickness, is nothing but the momentum deficit, non-dimensional form of the momentum deficit. Now if you calculate this value will always comes out to be positive. So that means the momentum thickness will always be positive, and that means that the momentum deficit is basically positive. That means there is always a loss of momentum as you go downstream of the in the boundary layer. So, so if I use the similar logic, so I can get on to this derivation of the mass momentum flow rate, and it is basically the reduction in the momentum that is basically there. Now, if I use these two quantities, so suppose if you have in the integral analysis part, now since both these delta star and theta are local dependent values of x, uh, I can express these in terms of length units. If you will see that the integral quantity is basically a non-dimensional thing, and it is integrated over dy, so that means it will be a non-dimensional thing. So now let us consider an approximate velocity profile where u by ux is nothing but f of eta. If since it is f of eta, I can write delta star as now, and eta is defined as y by gx. Now, if I can write a delta, therefore I can write the delta star equal to g times of 0 to infinity 1 minus u by u infinity d eta. Similarly, I can write d eta, theta also, where again gx is the scaling, and normally which we will which is equal to delta x, and eta is the similarity variable. Now we will use these in the development of the one common momentum integral equation. So we will consider a steady flow over a boundary layer over a flat surface, which is given by the first two equations. First equation. Now rearranging this, I can put it over here. Integrating this over dy. So the whole integrating the above equation, this equation over dy gets you these equations. Now, so the RH, let us calculate the RHS first. So RHS basically integrated over this. So it gives you del 2 u over del y square. It is there. So it is this is the integrand in the y. So I can write it like this. So we mu naught del u over del y 0 to infinity. Now 0 to infinity, at the infinity, that is outside the boundary layer, there is no viscosity, no velocity gradient present. So therefore it will be 0, and so I can write this as this, and which is now, since mu naught times of del mu dynamic viscosity into del u over del y is the wall shear stress, so I can write it like this. So that is minus times of 2 tau wall over rho. Now let us take LHS. So LHS, I can integrate the first term in the second term in the LHS, that is V into del u by del y. I can write this this integrate this in by parts, and if I substitute the continuity equation over here, I can write it like this. So the first term, the first term term becomes using the continuity equation. So u into del u by del y. Now LHS. Now if I substitute this back into the equation, this equation, I get this, that this is equal to 2 times of u into del u by del y plus minus u infinity du infinity by dx. Now this LHS can be then readjusted like this, as you shown, by adding and subtracting del u over del u by del x times of u into u infinity. And similarly, LHS can be thus modified these ways, and which has been shown over here. And so finally, the LHS becomes minus d by dx of u infinity square theta into delta square u infinity into del u infinity by del dx. So the one common momentum integral equation becomes d by dx of u infinity square theta u into delta theta into u infinity du infinity by dx tau whole by rho. Now if you will see these terms, the first term of this equation is a function of x. Second term is also a function of x, and the wall shear stress is also a function of. So locally, these are all the functions of x. Now for a zero pressure gradient boundary layer where u infinity is equal to u naught, so du infinity by x is 0. So therefore, so the momentum integral equation reduces to del theta by del x tau wall by rho naught into u infinity square. The one come now. There are two things which is very important to say about the common momentum integral equation. We have not yet put in any assumption on the fact that whether the flow is laminar or turbulent. So this one common momentum integral equation is basically valid for both the laminar and turbulent terms, turbulent flows. Just that you need to adjust the wall shear stress. Then it will not be only molecular. It will be based on both the molecular as well as the and the empirical value of mu naught. Mu naught. So let us use these approximate analysis. So in the approximate analysis, we basically suppose the velocity profile, and we try to develop this velocity, satisfy this velocity profile with the all the boundary conditions that are possible to satisfy. So let us capital H eta as the velocity profile, and if you have eta less than 1, then it is the H eta. If eta is greater than 1, that is outside the boundary layer. Eta is defined as y by delta x. Now if eta is greater than 1, then the velocity profile is 1. But if eta is less than 1, so the approximation basically comes over here. Since eta is only eta is at eta equal to 1, the velocity profile absolutely becomes equal to u is equal to u infinity. But if you remember from the differential analysis, we gave that at the boundary layer thickness, it is only 99% of u. So the approximation comes over here. The fact that this integral analysis uses very fast is a very fast method for getting an approximate predictions of this velocity of the integral quantities. It doesn't bother about what happens inside the film, so it cannot give you the cannot give you the variation on the velocity profile, but you can suppose the variation of the velocity profile, and if you are able to suppose it correctly, then the prediction of wall shear stress, skin friction, boundary layer thickness at all x stations can be obtained. Now let us first see that what are the boundary conditions which needs to be satisfied. Now for all of you students, this is very important. So the boundary velocity I have written. So you can h eta, eta can be any function of h of eta. It can be parabolic, it can be sine, trigonometric, it can have many components. It can have it can have more than five constants. So the equation can be of any constant behavior. It can be of any type. So the all the constants which are there in the velocity profile must be evaluated by using the boundary conditions. And the listing am going to give you for the boundary conditions, it should always follow the same thing, because these boundary conditions needs to be satisfied. The more the equations are there, more the number of parameters are there, the better is the equation, better is the approximations. And um, mm, so if the approximations of the velocity profile is better, then the boundary then the prediction in the of the of the quantities, integral quantities, will be better. Now the most important thing is that it must satisfy, you must satisfy the boundary conditions, these boundary conditions, in the order they are given. So the most important boundary condition which has to be satisfied is that the no slip boundary condition. That means that at the plate, that is y is equal to 0, velocity, u velocity must be equal to 0. So therefore, that means at eta equal to 0, h of eta, h at 0 must be equal to 0. Now the second most important thing is that the velocity must become equivalent to u infinity at the boundary layer thickness. So u should be equal to u infinity at the boundary layer thickness, that is at eta equal to 1, h of 1 must be equal to 1. Third important is that the velocity must vanish at y is equal to delta. So that means at eta equal to 1, velocity gradient must vanish at y is equal to delta. So at eta equal to 1, h prime of 1 should be equal to 0. Now the next conditions are there, these conditions, this is the fourth condition, and it must be satisfied for all non-variable non-variable outer flow. So if the outer flow is constant, outer, and that means the inviscid flow is not a function of x, then this condition must be satisfied, and that is that the second order velocity gradient at the wall must be equal to 0. So h double prime at eta equal to 0 must be equal to 0. Now let us take this example further and assume any velocity profile. So if you want to choose um, any velocity profile, let us take a parabolic form. And as in the parabolic form, I am taking, if you want to use a non-uniform velocity profile, outer flow, non-uniform outer flow, then you need to only choose the minimum choices of the ABC, that is the three variable, three constant. So that means so quadratic equation you can choose. But if you want to have a non-uniform outer flow, because the boundary conditions is such that then at that case there will be four boundary condition needs to be satisfied. So the equation, a polynomial equation, must have four constants. So that means a cubic equation needs to be satisfied. Okay, so now if you consider this, so let us consider a case for a uniform out of profile, and we will assume a fourth order, cubic velocity profile. That is a times of beta, a plus b of eta plus c of eta square plus d of eta q is equal to the u by u infinity, where u infinity is not a function of x. Now eta is defined as y by delta x. If when eta is less than 1, so if it is greater than 1, then the value of u by u infinity is 1. So if you satisfy these boundary conditions, so a will come out to be 0 from the first boundary condition. Second boundary condition, if you will satisfy, then a plus b plus c plus d is 1. If the third boundary condition, then b plus 2c plus 3d is equal to 0. And if you satisfy the fourth boundary condition, c becomes equal to 0. That means a and c are 0, and that means the constant term and the square term in the polynomial is 0. And b and c comes out to be b and d comes out to be 3 by 2 times of eta minus 1 by 2 times of eta square. B comes out to be 3 by 2, and D comes out to be minus 1 by 2. So the cubic velocity profile comes out as 3 by 2 times of eta minus 1 by 2 times of eta cube. Now this satisfies the uniform out of flow conditions. So let us use this equation and evaluate what is theta. Now if you, and I will just substitute over here as it is shown over here, and theta comes out to be equal to 39 by 280 times of delta. Okay, and similarly delta theta star will come out to be 3 by 8 times of delta. So you can see that both of them are functions of x, as delta is the function of x. Now if I substitute this in the wall shear stress, it comes out to be 3 by 2 times of rho into u infinity by delta. Now rho and u infinity both are not functions of x. Delta is the only function of x. So I can say that again the wall shear stress is the function of x. Now using the von Neumann momentum integral equation, del theta by del x for the uniform outer flow, del theta by del x becomes equal to tau all by rho naught rho into u infinity square. So this equation, I will substitute these quantities over here, and I get that the delta square is equal to 280 by 30 mu x square by u infinity into x. Now from this, if I multiply and divide by x and modify and put Rex, use the definition of local Reynolds number, that is Rex. And now Rex is equal to u infinity x by nu. So this comes out to be 4 by 64, 4.64 Rex raised to the power half. So now if I substitute this into the wall shear stress, so this gives you a prediction of how the boundary layer thickness is going to vary with x. Now if I substitute this into the wall shear stress relationship back, the delta variation, that is 4.64 Rex raised to the power minus half, x raised to the power half, I can get the relationship for the skin friction, that is 0.6464 Rex raised to the power again minus half. Also if I integrate this, then I can get the drag relationship, and that this comes out to be 1.3528 into Rex raised to the power half again. So you can see that by doing this very simple approximate analysis, and I can obtain the first estimates of skin friction, first boundary layer variation of x, boundary layer thickness variation with x, the skin friction, wall shear stress, and the drag coefficient. So for an engineer to design, you just need these drag coefficients and skin friction for the design. So now if I let us compare these things. So the Blasius solution, which was shown in the last lecture, gives you that delta by x basically varies by 5 times of Rex raised to the power minus half, whereas the delta by x by the approximate solution is 4.64 Rex raised to the power minus half. If skin friction compares, so you can see that the coefficients slightly vary, but the variation, local level variation with Reynolds number comes out to be entirely correct for both the skin friction as well as the drag. And you can always know that since it is an approximate solution, if you consider more or the better or the with more constants, the velocity profile, this will be a slightly more accurate prediction. So you can always increase the accuracy. Now I will leave you with this question, that which is the more accurate in comparison to the experimental results, and why. So you need to think about this, and I think I am pretty clear in my lecture that who should be the more accurate solution. So thank you, and this completes your boundary layer chapter, and this will help you in further reading. If you need to ask any questions, please ask. Okay, thank you.